something I want to pivot back to is just when we calculated this final separation equation here. I just wanted to highlight a potential mistake that students might do, because I for sure have done it. Let me just write it out. So let me just go back and write that first setup that we had, which was 1/2 mvi squared plus k, the charge of the first particle, charge of the second one, its initial separation distance. And remember, kinetic energy, we don't have none, there's no final kinetic energy, and then we do have a final potential energy. So this is the law of conservation of energy that we wrote earlier before we solved for RF, and I'm just writing this out here to show just a common mistake. But so we don't get confused, I'm going to just write it out so that, oh no, it's just, geometry. We'll section this off. Alright, so I sectioned out this corner here just so that y'all don't get confused with the actual correct answer stuff here, but I just want to show you a common mistake that might be done. So for me, and I'm sure many of y'all, a common mistake that happens is you're used to, if you see a fraction, you just want to flip it if what you're interested is on the bottom here in the denominator. And that does work out, but you need to be careful. And so I'm just going to follow through with the mistake, and then I'll go over it to see why it doesn't work. And so, let's just follow what we want to do. So we want this to be in the numerator. We want this to be on top. And so let's just flip it, right? And we flip these terms. So RF's on top, and then K and those Q's are at the bottom, similarly here. And then we'll 1 over this. So we'll write it out. We flip them. The initial squared, and now we get our initial here. Finish these two out, and then now we get our final separation distance on top. Alright, so now we flipped them, right? We got RF, which is what we're trying to solve for, the separation distance on top. And now we need to get rid of this denominator here. And so to do that, you just multiply by KQ1, Q2 over here, and they will cancel. Then over here, can't forget about the parentheses. So you got to distribute out the term. Q1, Q2. Alright, and now we have solved for the final separation distance. I'll write it out over here. We'll put it on the left side this time. Alright, and now we distribute these out. So we'll get K, Q1, Q2 over 1/2 mvi squared plus Ri K, Q1, Q2 over K, Q1, Q2. And you're like, whoa, amazing. And you're like, oh, I could cancel these now because they're the same. These values don't change. And that leads to a final formula, or so we think, just to make sure we know this is a common mistake. So I'm about to do a gotcha moment. But before we get there, there we go. Now we've solved for our final. Now, you may have already caught on to the issue by now, or if you didn't, then this is perfect for you. But the biggest issue here is when we flipped it, these terms are being added up together, and it's not true that they would be the same value when flipped. If you were to try to do this approach, you would want to combine this to be one fraction, and then you're allowed to do that flip it trick. And so what you would have wanted to do was multiply the top and bottoms of this term with Ri, so then you could put this to be a single term and be one fraction. And then this flip it trick would work. Another way to think about it, if I just write it out on like a more simpler way on why it wouldn't work. Let me just take up this space so I could show you why this doesn't work. Is that it's just like maximize this box. Alright, so let me just show you why this doesn't work. If describing this, making this one fraction doesn't make sense. So another way to think about this is imagine that we said A plus B equals C, which is fine. And then if we follow through with exactly the steps that we did here, we said that 1 over A plus 1 over B would equal 1 over C. And you're like, okay, I mean, looks reasonable so far. And now let's give these values. Let's give A, B, and C some values. And so if we say, let's just say A was 2 and B was 3. So here, 2 plus 3, quick maths. You pull out your calculator if you need to. Hopefully you don't. But it's all good. We get 5. And we're like, okay. And so then that must mean then if we know these are the values of A, B, and C, then we state over here that 1 over 2 plus 1 over 3 is equal to 1 over 5. Now, let's just think about this. If you have half a pizza and another third of a pizza, that's a lot of pizza. And it would be weird that it ends up with you have a fifth of a pizza. That doesn't just make no sense. Right? Or you could think of it like you have 50 cents and 33 cents. Why does that make 20 cents? This is where the issue is here. And so that's why this whole thing that we wrote out here does not work and doesn't hold true. So if you were doing that approach to solve for RF, I'll go back to this just simple setup here. The correct way, I'll write it outside the box, because that's, this correct stuff out here. It would end up being that 1 over A plus B would equal 1 over C. It might seem a little subtle, right? It's just a difference, like where you put the plus sign and like what's it over. But this here holds true. This is correct. Because if you look at our own example here, A is 2 and B is 3. That makes 5. And we said C is 5. So you would get 1 over 5 is equal to 1 over 5. And that would be the correct way to actually do the flip it nature of these fractions to then solve for RF. So if you wanted to, you could go back, resolve it, and for A, plug in the kinetic energy term, and then for B, you would plug in the initial potential energy term, and then for C, you would plug in the final potential energy term. And then you could go through a similar solving process here, and you should end up to a correct RF, describing the separation distance. And so now you got everything you need, and let's just clean up this board.